We start. Let's go. I will start recording, Anna.
Yeah.
Okay. Good morning, everybody. Welcome for this new colloquium, in this case, web colloquium, from the Instituto de Astrofísica de Andalucía here in Granada, in Spain. And today we will have the talk by Dr. Ana Neles, and she will talk about moving from high to extreme precision in air shower observations from LOFAR to SKAO. Dr. Neles will be properly introduced by Isabel Marquez. Please, Isabel.
Thank you, René. Good morning, everybody, or good afternoon. And thank you very much for participating in this new colloquium in online format this time for the Severo Ochoa program. And so first of all, thank you very much, Ana Neles, for having accepted our invitation. It's a pleasure to have you here. And just for you to know, Ana Neles is a professor of astroparticle physics at the University of Erlangen-Nuremberg and scientific staff at DISI Research Center in Germany since 2019. She made her master's in physics from RWTH in Aachen in Germany, and in 2014 she got her PhD in astrophysics at Radboud University Nijmegen in the Netherlands. All difficult names for me to pronounce. Afterwards, between 2015 and 2018, she got a postdoc position at the University of California, even in the United States. And between 2018 and 19, she was the estimator group leader at the Humboldt University in Berlin, in Germany. Her research targets are astrophysical particles of the highest energies. In fact, she's a specialist in the radio detection of neutrinos above Perth energies. Her group is currently constructing the most sensitive neutrino array to date, the Radio Neutrino Observatory, RNOG, in Greenland. With her background in radio detection of cosmic rays and software development, she pushes for the next generation radio experiment in the polar regions, such as planned for IceCube Gen 2. She is also affiliated with the Cosmic Ray Project of the LOFAR telescope, where they detect cosmic rays and lightning and work in the high energy focus group of the Square Kilometre Array, the SKA. In this talk today, she will report on ongoing efforts with this high energy focus group towards preparing for high energy particle measurements with the SKAO, starting from previous experience of gathering air shower observations with record-breaking accuracy with LOFAR. As I said at the beginning, it's a pleasure for us to have Professor Ana Neles with us, and the floor is yours.
Thank you very much for this nice introduction. Yeah, so today, I have a neutrino side of me and I have a cosmic ray side of me. And today, the cosmic ray side will talk, and it will focus on something that we've been sort of thinking about and working towards for a while, of doing this with LOFAR and then moving towards the SKA. And for those of you, who are used to maybe more SKA talks showing you beautiful images that SKA can do, I thought I'll show you a top-down view of the technical things of SKA low in Australia. And this is sort of what our work will focus on. And I just wanted to highlight for you sort of this incredible antenna density that we'll see out there in the field. And this is the engineering station for SKA, so it's not even the big one yet. So it's going to be very interesting sort of for us, this technical detail. And you'll see sort of every little dot you see with this triangular shade. This is one of the SKA low antennas that we're using for our air shower business. So let's get started, and let's start a little bit with the scientific motivation. And I always know when I talk to astronomers, I sort of, if I go talk to my neutrino friends, they all know this figure and go, yeah, don't say this again. So, but for many of you, this may be a somewhat new figure. So let me go through this briefly. This is what we call the multi-messenger picture. So we have on the y-axis, we have the all particle flux scaled with energy squared, and as a function of particle energy on the x-axis. And what you see there is the gamma ray background as measured by the Fermi telescope in red at the lowest energies. Then in the middle, we have high energy neutrinos as measured by IceCube, the astrophysical neutrino flux. And then on the other side in orange, the cosmic rays as measured by the Pierre Auger Observatory. These are just two highlights of the world leading observatories. And what's become sort of, what I'm highlighting here, of course, is that there's a big gap between the neutrinos and the cosmic rays. And that just means that neutrino measurements are not sort of as high in energy as they could be. So this is something that the community has set out to discover, to discover the high energy neutrinos. Why do we do this? This is because cosmic rays at the highest energies, it's even though they've been measured for a very long time that we have cosmic rays of these extreme energies, then we're not quite sure yet where they come from. So the nice thing is that they're related. So, if you want to know where these cosmic rays come from, what you can do, you have two alternatives. You have one alternative that says you can measure more neutrinos, because for every cosmic ray that's produced at the side, the many cosmic rays at the same side will interact with surrounding media, will make pion production that produces neutrinos. So if you're interested in where are the sources of ultra high energy cosmic rays, you could measure the neutrinos. And the neutrinos, since they're neutral particles, they travel in straight lines to you. So measuring neutrinos would point you to the sources of ultra high energy cosmic rays. So you could do this. So this is what my one half does, but you can also do the other side. You can measure cosmic rays with better precision. And this is where this talk will focus on today, is sort of how do we measure cosmic rays with better precision, and how do we get to a point where this may actually help us understand the sources and pinpoint the sources and how we do this. So this is where I'm scientifically coming from. Sort of my work really centers around finding the sources of ultra high energy cosmic rays, and finally putting this to rest, that sort of whenever somebody claims something that people go, but there are theoretical arguments against this, so we need better data. I'm an experimental, really an experimental person, so I build the detectors that hopefully help us get there. So how do we do this? Let's start with something. So, I talk about SKA, so I talk about radio, and I do not use sort of SKA or LOFAR to make images of galaxies and other objects. I use radio signals by cosmic rays when they interact the Earth atmosphere. And that is even though it is classical, it is sort of quantum electrodynamics, it's not classical textbook physics. So let me start with what happens there. So you have a cosmic ray that comes in, and the cosmic ray has such a high energy that for the cosmic ray, a charged particle, maybe a proton, maybe an iron particle, we're not so sure, that comes into the atmosphere, and it has such a high energy that the atmosphere is not transparent. So it will basically crash into an air molecule and into a nucleus, and it will make what we call an air shower. And that's just a cascade of secondary particles. And in every one of these showers, you always have a hadronic component, and that's just your protons, your neutrons, and sort of all the hadronic QCD stuff that's going on. Then you always have a muonic component. Those are the muons from air showers. And if you have a spark chamber or something in your institute, all the nice little tracks you see there are the secondary muons from air showers. And then every shower has an electromagnetic component, and that consists sort of from neutral pions decaying. You will get gamma rays and electrons and positrons, and these form an electromagnetic shower. And every shower of an air shower has this electromagnetic shower, and this electromagnetic subshower gives rise to radio emission. How does that happen? So you need, and we know this now very, very well, which is quite nice, you need 3 ingredients for this to happen. And I'll give you a brief overview and then go into a little more detail. So, when you have a shower, you need 3 ingredients, one being the Earth magnetic field. So when you have a shower come down and all your electrons and positrons in your shower, they feel the Lorentz force, and then sort of one half goes to the left, so to say, and the other half goes to the right. That's one ingredient. So, then you get a charge separation, and that already sounds a little bit like electrodynamics and potentially radio emission. Then you have the next thing, and that's a particle physics process where you get a charge imbalance, sometimes called the Ascarian effect in air showers, where your shower sort of develops in the atmosphere and it sweeps up electrons from the surrounding medium. And so then your shower front ends up being negative and the ions are left behind. Why only negative? Because we don't have positrons in our atmosphere. So there's no positrons that the shower could collect. So it only collects the electrons. So again, here you get a charge separation that comes to it. And then you need, in order to fully understand this, you need to take into account the index of refraction, because in air, even though it's very, very close to 1, the index of refraction is not precisely 1. So that means that you get sort of compression effects at the Cherenkov cone that sort of where it can lead to the fact that the shower is actually faster than its emission. So if you look at this figure here in the geometric path, it's quite clear which one of these two paths is slower. But in time, it actually may be that this one that looks much shorter here is slower. So those three ingredients do we need. So what happens there in detail? Just to go over this again. So for the geomagnetic effect, you have an incoming particle in a magnetic field, and depending on its charge, by the Lorentz force, one goes to one side and one to the other side. If you just have a single particle, not a lot happens. But if you take many of them, you sort of take you just think of it as, okay, this happens in your shower, and then in the shower sort of gets a negatively charged and a positively charged half. That whole thing, this charge separation that you get is a number of particles as a function of height above the ground. And here's sort of something, just a little sketch of this. So you see the number of particles as a function of distance traveled through the atmosphere, and you can see sort of how they'll get a lot and then they decay again. So this whole thing, what you basically have, you have a dipole developing. You have a dipole, that grows as you have many particles and move out, and then it sort of decays again, this dipole. And this changing dipole, you can also model as a current, and the current changes as a function of height and time. And a changing current always causes electromagnetic emission. So, and if you take into account the time scale of this shower happening on a nanosecond scale, you sort of get nanosecond pulses and electric field change. Then you have the second part, and that is sort of what I call the Ascarian effect. So you have many numerous high energy photons in your shower, and the photons can just kick out electrons that are in the medium, and then sort of basically by this particle physics effect, you have an incoming photon, an outgoing photon, and then an accelerated electron that joins the shower. So if you do this along the shower axis, it's the same picture of a dipole. And of course, the more particles you have in your shower, the more photons, the more electrons it can grab along. So it's a similar thing as a function of height and time. So then you have a current in this direction, sort of that grows and shrinks again. Again, you get induced electric emission that's sort of on a pulse level of a nanosecond timescale. And then on top of that, sort of just another depiction of how your shower can be faster than its emission, because the index of refraction in air, it's say 1.003, which is, if you're at the speed of light, means there's significant room for particles to be faster than the speed of light. So when you then think of it, is sort of if two signals that you have arrive sort of out of phase, they'll just cancel out. That means if you take all these travel times into account, then there's a region where there will be no emission, and there'll be a region where there's enhanced emission. And the enhanced emission will happen precisely at the Cherenkov cone, at the Cherenkov angle. So that's how the Cherenkov angle actually is defined, as in this medium where you'll have signals arriving in phase. So my two different pulse mechanisms have to be folded with the fact that you get some enhancement at the Cherenkov angle where they all the signals arrive in phase. So let's puzzle this all together. So it's rather complicated. And when I started my PhD, I've been literally given the advice, like, why do you want to move into a field where theorists are arguing at conferences and fighting over which emission mechanism it is? And, it was very diffuse. And, apparently I was naive enough to think, it's going to solve itself. And it did. So a couple of years into my PhD, with many of the LOFAR results we had, sort of all the theorists were like, oh, okay, I guess everybody was right. All the emission mechanisms play a role. So if you think of this now, it's sort of, we have the geomagnetic emission that I introduced, and we always use this very particular coordinate system that has V cross B, so the Lorentz force axis, as one axis, and then V cross, and then there's brackets missing here, V cross B on the other axis. So we have this coordinate system that is defined by the shower axis V and the magnetic field B. And why do we do that? That is because the polarization of the signals that are emitted is along these particular axes. So for the geomagnetic effect, all the emission, the blue arrows, are along the V cross B axis. For the charge excess, however, because it's a rotationally symmetric problem, there's nothing, in particular, only along the shower axis, the emission actually points towards the shower axis. And if you do vector addition here, and everybody can do this, sort of, those two actually add up in the same way, on the other side, they sort of add up destructively, you can get used to how we plot air shower footprints. So this is in an air shower. You point basically, you're on the shower axis, and the shower axis points into the field here, and you see the emission around here where dark is the strongest, and it goes to white for the weakest. And you see sort of this oddly bean-shaped position, bean-shaped thing here, which is just a result of this vector addition of, on one side, you see more and less, and that combined with a Cherenkov ring. So the details of this shape, so it's a very complex shape, and if you're from air shower physics, you're used to much smoother distribution. So this is very weird, two-dimensional shape, complicated. But the nice thing is that the details of the shape can be used to measure air shower characteristics, parameters, at very high precision. And that's why it's worth sort of understanding all this complexity. So let's jump right into air shower business. So, I wanna just face this question right on. Are we really sure that we have understood this? It happens still to me from time to time that people who've been around in this field for a longer time and sort of maybe haven't had the chance to follow the recent progress, essentially just remember discussions from, say, the early 90s or the early 2000s, even saying, why do we even do this? You can't possibly be sure that you've all understood this. So, but I think right now I can say we have quite a lot of experimental evidence that what we simulate in our calculations is precisely what we measure on the ground in our instrument. And LOFAR really has been the instrument to do this, because LOFAR has such a flurry of antennas that we can actually do this. So this is at the top, you see one of those images that has LOFAR. And every LOFAR antenna is one of those little dots here. And in the background is a simulation of what we think we should see. And wherever the color of in the dot and in the background, wherever they match, we have perfect agreement between simulations and what we measure. And you see the sort of, just to give you an idea, a typical air shower array, so like the Polarization Observatory or so, would have like 2 points in this plot. And clearly with 2 points, you have so many degrees of freedom, like how do you move your shower, where do you go, that you'll have a hard time actually proving all these detailed features. And only with LOFAR, if you not know what you're looking for, it's just very good to have a lot of antennas. We've been able to show this. So this is the signal distribution really looks like microscopic Monte Carlo simulations like Corsica and Koreas tell us they should. So if you looked at the signal distribution and the amplitude, we've also looked at polarization, and that you see here on the bottom, the little arrows, all the little arrows point roughly in the V cross B direction, but you see a slight deviation, and that is sort of the Ascarian effect that you see. We looked at higher frequencies. So in the middle figure, you see the LOFAR high band antennas. So they are slightly differently distributed. So you don't have the dots like they are in LOFAR, but you have little clusters of the high band antennas. And at higher frequencies, the Cherenkov cone is much more pronounced. And then we've looked at also circular polarization, which is finally shown there. That also told us everything. So LOFAR really has been the instrument for us to learn how to do this. So, and the key evidence is polarization, because that is geomagnetic effect and Ascarian effect on top of each other. Again, here just a little different graphic for the vector addition. And here the two plots even in sort of a bit more detail, where you can see, okay, the nice match. And you can also see that sort of, if here's 0, that's where the point is. The 0, 0 is the shower of the center of the shower axis, and you basically see above the 0, 0 line little arrows pointing upwards, and above the 0, 0 line you see little arrows pointing downwards. So with LOFAR data and with full polarization reconstruction, we can see all these interactions. And that's not all of it. I mentioned circular polarization, and how that happens is we have linearly polarized signals, but not quite, because the two emission mechanisms that we have, they stem from slightly different heights. And if you do vector addition, sort of with a little time offset, and then it's sort of, my vector addition problem boils down, because of course it's oscillating electromagnetic waves. But if you give them a phase, then all of a sudden it's no longer linearly polarized, but elliptically polarized. So if you have a small fraction of circular polarization, and that is also what we've been able to measure and show. So you see here Stokes V, a Stokes V map on the same axis. And again, the colors in the circles match very well the colors of the background. So we've been able to firmly establish that the emission is both due to geomagnetic emission and Ascarian emission, and that Ascarian emission is an air a 20% correction, if any. That is different for neutrinos, but that's also a different talk. And it was discussed sort of early on that geosynchrotron radiation may be actually the dominant part. That is at the low frequencies where LOFAR and others operate. This is a correction of 1% to these effects. It may become much more relevant at very inclined air shower geometries or very, very high frequencies. But for the time being, we've also been able to put this to rest. And this is, again, in degrees, sort of this Cherenkov ring that you see here. It's sort of, I think it's super nice. When we saw that, we were like, oh, finally, we understood it. But something I did want to point out, because many people see sort of, they see these Cherenkov rings and they say, oh, you see a Cherenkov emission, like, you know, from a little, like from a muon when it flies to a swimming pool or so. This is really not Cherenkov radiation, because we would have exactly the same emission. So our showers, if you could do that, have a particle shower in vacuum, which has sort of some other problems. But if you have had a particle shower in vacuum, where it's sort of index of refraction perfectly 1, we would still see emission. So it really is a particle physics effect or a shower physics effect that makes these. You don't necessarily need the fact that your shower is faster than the speed of light. It only compresses the image then there. Okay, this all was fun and games, and you know, you're now like, oh, you know, this is complicated, and probably kept a bunch of physics interested postdocs and PhD students busy for a while and all excited. But yeah, there's time to grow up, and I think so. What we've really been with all these early experiments, and that's not just LOFAR, that's also Ayera, Lopez, and Kolalema and other friends. We did provide the proof of principle that radio detection of particle shower works. We did confirm the emission mechanisms down to the subtle features. There was lots of fun with polarizations and other things. And we developed lots of methods of how to reconstruct the data, remove noise, understand antenna theory, and all sorts of things. So there was a lot of method going on. But the technique in itself is really only useful if you can contribute somehow to advancement of physics. I mean, understanding the emission mechanism also is advancement of physics. But really, sort of, we want to learn about the cosmos. So we want to know, can radio detection help us get a better cosmic ray energy spectrum, which we could then use as input to studying particle accelerations in sources, which would then help us to understand sources of ultra-high cosmic rays. So these are really the questions that are driving us. And that's where radio, the question is, does radio detection help us there? And the nice thing is it does. So if we radio detect an air shower, if we take the radio signal, like this beam chain pattern on the ground, if we detect it, we can have a very excellent energy estimator of the original particle. And for those of you sort of maybe having heard about this, so energy reconstruction is always hard with particle detectors because there are these hadronic interaction models. So the particle physics in the shower is not sufficiently well known to actually be able to understand all of these in detail. So what we've done here for Auger is we've taken Auger radio. So this is on the y-axis, the radio energy estimator as a function of the energy estimator of the particle detector of Auger. And you see a lot of scatter. But the interesting thing is that the scatter can exclusively be explained by the energy uncertainty of the surface detector, of the particle detector. So radio has to be much, much better than the particle detector, also experimentally. And from first principles, the method itself and the calculations, like there are not any free parameters unless we believe that our understanding of electrodynamics is wrong. So from a method point of view and simulations point of view, there are very little systematic uncertainties in the energy of less than 5%. So this is really great. And we've, insofar as it was experimentally possible, we've also proven that the simulations do depict reality. Let me mute myself real brief. I somehow have managed to catch a cold. But since I didn't have to travel for this seminar, that makes it now easier to continue here. Okay, so we've shown this from simulation, and what could that do? That could actually help us to reduce systematic uncertainties between observatories. So for instance, at the most ultra-high energy range, we always have the problem that the telescope array in the northern hemisphere and Auger in the southern hemisphere, they are in slight tension, and then they look at the details and they see that ultimately all the systematics on the energy scale may explain all the details. But then theorists come to us and say, look, it's all, you know, nice that you as experimentalists have all these systematic uncertainties, but we really would just like to have one spectrum that we can use to put it into our models and not, you know, always think about additional systematic uncertainties that might be there. So with radio, you could do this. You could beat down many of these systematic uncertainties. And so we've just done a proof of principle work here where we've taken the Auger energy scale, which is the green one, and plotted on top of the LOFAR energy scale, the purple one, just for consistency, and you see they all match up. So this is, you know, very early work just showing you that that works. And my colleague Catherine Mulray is actually working on an array that we may bring to these observatories to do this on a high precision base. So that would be great for radio detection. So energy estimation is great. It is also great that the radio pattern is very sensitive to the particle type. And I always say X max, that's sort of our parameter, but basically that's a proxy for the particle type. So you see this here geometrically, it's sort of, if a shower is higher, the footprint is larger and more spread out. And if it's closer, it's sort of smaller. And basically we can say on average, proton particles go deeper into the atmosphere. So they're closer to the ground. So they'll on average be smaller. But also have more spread. So, and then sort of, you know, you can basically by saying on average statistically where they are, where you would sit. So then here, this is illustrated. You can see here, these are sort of the world measurements. And this is the predictions for iron are the red lines. So this is a function of energy, this max parameter, and the proton predictions are there. And the world measurements are somewhere in the middle, which is, you know, it just means some mixed composition at the highest energies. But if you look at the details, the interesting thing is that the blue points from LOFAR and the black points we've published earlier, they're actually a little bit in tension to these stars here from Auger, which is the world leading measurements. Nobody really knows why, but the one difference is, of course, the methodology, radio versus fluorescence detection, but it's also northern versus southern hemisphere. So there's maybe potential for a radio measurement on the southern hemisphere to see whether the Auger measurements can be reproduced, and it may still be something related to the hemisphere. How do we do this? Let me just show you this real brief to give you an idea better. The estimator of the mass. So if you have a proton that, for instance, would make, you know, such a footprint on LOFAR, this is the central LOFAR core with all the antennas. And if we had this in iron, that would make maybe such a footprint. So, but what we have is just the data there. So what we then do is for every event that we've detected, we make 30 simulations that covers the entire range of options for our shower maximum. So we simulate all of these footprints 30 times. And we fit this to the data, including all sorts of system responses. And then we optimize here. This is a reduced chi-square fit. We look for where is the optimal X max that describes this. And this is sort of then for the fit how you do this. It gives us a very good estimator for the mass, but it's currently very brute force and computationally expensive because every one of these simulations takes a week. So this is also due to the fact that the LOFAR antennas are so oddly organized that sometimes you just miss having them on the right corner of your shower and these things. So you need lots of interpolation and lots of work to do. So an array with better antenna coverage would allow for many more elegant solutions at this point, which again is another hint why we may like the SKA. So what are our future plans with LOFAR? So right now, LOFAR does provide world-leading measurements in air shower composition that are sort of interesting for theorists, but we want to increase the statistics. And since at LOFAR, people are very worried sort of about us, you know, not reading data directly, we have to send triggers, and we send these triggers by a particle detector array. And this particle detector array is sort of has currently been enlarged, and it's being commissioned right now, so that we may actually be able to get better data. And then there's this whole LOFAR 2.0 project in which we could even envision using low band and high band antennas together. So there's still a lot of stuff going on at LOFAR, and I'm excited for this to go forward. But let's look at sort of the global neighborhood of what's going on. You see here in blue, you see LOFAR. And the other ones are sort of, I mentioned this before, many of them are the dedicated air shower arrays. So you see this here, like Kodalema was one of the early ones. Lopez was very small. And you see in green, you see Aera, it's one of the bigger ones, but you see there, all of them, they're very, very sparse. So in a way, LOFAR and even more so SKA, they're very different. But that's, of course, what also makes them exciting for us, a very different instrument. So this is my air shower detection with the SKA. And I think, after this, I can just stop because it's just, for us, it's just going to be insane. But insane at the same time in a scary way and in a good way. So because this is the exact same air shower simulated for LOFAR. And if I ask my colleagues at Auger, they'll already tell me, oh, LOFAR has an insane amount of antennas. And the bottom here, it's for the SKA. And while the small figure already looks nuts, you zoom in and you realize, oh, every one of these big points is actually a station of so many antennas. And that means all this interpolation and putting things in the background and seeing how this works, I can give you pictures, and by eye you can tell me like, oh, this one works, that one works, the other one works. So this is basically just having simulations like these tell you why SKA will move air shower observations from like great high precision to ultra high precision. I don't even know, I'm running out of adjectives to go there. So what will we do? So that is next to more antennas, that was very obvious. SKA also has a much better frequency coverage. So the LOFAR low band antennas only go from 30 to 80 megahertz. The high band antennas have a couple of very technical details that don't make them so suitable for us. So we basically restricted to 30 to 80 megahertz. And with the SKA antennas, we could get 50 to 350, which would be great. There are many things in the frequency slope that we could study. The SKA has enough antennas to actually use the raw data directly. As I said, no interpolation, no fitting. And this is done here by one of my colleagues. He just plotted all the SKA data points of a simulation on top of each other. You can see the bean-shaped footprint. You don't need an interpolated map in the background. It is an extreme challenge for cutting-edge data science, though, I have to say. It's sort of, it's not going to be easy. Already handling the simulations taught us a lot about, we cannot do this anymore. This is too coarse. But there's so much more in the signal. We just use Xmax as a proxy because we can't do any better. But a shower actually may not be smooth. It may have a first interaction that's clumpy. It have other things. So there's many more things in there. And this is going to be very exciting. So we could use it for more precise access to the cosmic ray composition. So right now, I can tell you that it's a mixture between proton and iron and probably has a strong proton component, but that's roughly about it. But if I were able to tell my theory colleagues, look at this energy, you have 5% protons, 10% helium, and the rest is, I don't know, oxygen or so, they will be very, very excited. So that would be great for astronomy. And then on the other side, it could also give us an independent handle on all these hadronic interaction models that I talked about, sort of all the QCD stuff that happens in the shower. There are many free parameters in there that you can tune. So if we were able to give people like a nice detail of the shower development and an energy in these things, they would have a much easier time looking into particle physics that is really not probable like accelerators because it's so high energies. Our showers are orders of magnitude more in energy than what the LHC can deliver. So it's cool and direct for particle physics. So I have to say right now, I cannot give you super many details about what the work it is, because right now all our methods are sort of work in progress, because we've sort of been using LOFAR methods and then realized, oh my God, all our methods are really not suitable for SKA. So we're developing method and science case at the same time. But I'll, some of it is also a bit speculative, but let's give you an idea. So this is also the shower that we talked about. And this is, again, number of particles as a function of sort of shower development traveling. And you don't just have Xmax, which would be the point here of the shower maximum, but you have two parameters. If you model this, you can model it with more, but let's start with the two. You have a symmetry in there, sort of like, tilting it left and right, which is sort of one parameter, and you have a changing width. This is sort of how wide this is. And those are the parameters R and L. And in first order, the particle type is just correlated with the maximum of the distribution. But with the hadronic interaction model, you need these sort of all the other parameters to point this down. And this is some work by my colleagues in Brussels that show you that if you have Xmax and this parameter L, so that's the one for the shower shape, what you get here, you get these funny triangles. And you should remember sort of orange is QGS jet. That is one hadronic interaction model. And blue is Sybil. That's another hadronic interaction model. And the two bottom triangles are for an energy of 10 to the 17, and the two top triangles are for an energy of 10 to the 18. So if you have for a shower a perfect energy resolution, and you have a good X max resolution and an L parameter resolution, so we've known energy resolution we can do well, X max we can do well, but maybe with SKA we could add L to the mix, then you can precisely say in which triangle you end up here. And not only can you tell whether your shower is more likely to be a proton, like if you're here, but you can also tell whether it's, you know, more likely a proton or with more close to what QGS jet measured, or a proton more closely to what Sybil measures. So actually with these things, you're starting to split up your options. So if you have something in here, you know, and you're very sure about the energy, then you know something has to be wrong. There's all of a sudden, there's actually a change for us. So far, we've just been dependent on the hadronic interaction model. People just said, use one, and used it to interpret your data. But with SKA, we are not dependent on it anymore. We could help ourselves. So we've been trying to work with this. This is work led by Arthur Costagne. And it's we're using the old style LOFAR analysis, just brute forcing our way through it to get you an idea what we can do. And this is literally the plot we're making for one shower, one shower and then many incarnations of it. And what you see is that X max and an L and R combi, they there's a best fit for a shower that you can get. You see at this point, we need many, many more simulations in order to actually figure out what simulation has the best fit value here. But, you know, there's the old LOFAR style antenna. I'm fairly certain that we'll get smarter with the time, but this is a proof of principle that it does work. So we can not only reconstruct X max with SKA, but we can reconstruct an L and R combination. So this is certainly work ongoing, and this will make it very exciting for us to go measure SKA showers. What else? I think what I'm most hopeful for is that we could develop a 3D beamforming algorithm to reconstruct this. You know, this is a Corsica simulation. We could reconstruct it directly. That you could use the radio emission and not just beamform assuming infinity, like parallel arrival directions, but say that, okay, we have points in the atmosphere. So we really try to map out a 3D interpretation of a shower. Now, which is going to be, I think, really cool. But you know, it right now I really was like, how can we not just, you know, find out a 3D image? We can't do it right now. It's just so much data and the methods are still under construction. So, but I hope that in some future we can, at least from a simulation point of view, show you what we think we could achieve in a 3D beamforming. Talking about 3D beamforming, I really couldn't help but shortly digress into you really never know what's coming. So when we worked on LOFAR, we realized that actually thunderstorms, they influence our air showers. So when we measure air showers in thunderstorms, they don't look like they should, which is a long lesson about observer bias of us just going, oh, those are the weird ones, put them on a pile. I don't know. Until somebody realized, oh, all the weird ones are during bad weather. Oh, what happened? Oh, electric fields in thunderstorm. The electric fields interfere with our air showers. So that was great. So that was what got us interested in, so what happens with all this radio stuff in air showers? And then due to a couple of cool connections, we actually figured out that LOFAR is the world's most powerful lightning interferometer. So you see here at the bottom, you see a 3D image of a lightning strike. And this is the world's best resolution in time and space, and it's just great. And especially Brian Hare, my colleague from Groningen, who's leading this, is doing excellent work in actually understanding or answering many questions that have been unanswered in lightning physics for a long time, just because they didn't have the right instrument. And, you know, we just happen to be experts on how to use LOFAR. So that's how I, as an astroparticle physicist, ended up leading really answering atmospheric research questions. So it's super interesting. You can, you know, if you listen to Brian Hare, he could talk about this for hours. You have this very complex structure, and these are, you know, if you, you know, for all those recorded things, you can put on pause and you just ponder about this for a while. This is, you know, at east, west, north, south. This is a 3D image cube and then projected onto what you have there. And it's very, very interesting. You have this you have negative leaders, positive leaders, return strokes, and all these things going on. So we really published the first image of a lightning strike, which can resolve these positive leaders and all the details. There's so much going on. The drawback is, well, LOFAR is not really located in a region famous for lightning. So it seems that lightning depends actually on cloud structures. So we have a hard time comparing this to most measurements from Florida and New Mexico because the clouds are just different. So this is certainly a topic that's also worthwhile following up for the SKA, Australian clouds. Let's see what happens there. So that also would be really interesting. So one last bit of why this is complicated and why we actually need to understand so much about an instrument is that when we detect air showers, we search for a very broadband nanosecond scale pulse. It is typically detectable at PeV energy, so 10 to the 15, and that means you get, if you're lucky, you get 1 an hour. So we look for very rare bursts, but then if they come there, they are relatively strong signals, and you need at least sort of a sampling speed of 200 megahertz. You want full waveform sampling. You preferably don't want to burn so much power on this, and you can measure all the time during all weathers. And this is just showing you how technology has advanced. So this is how air shower radio signals were discovered in the 60s. You see here this little oscillation from the timing. You see a little clock that ran in the background. So, this is a photo. So they took every time they have a trigger, you take a photo and then you start counting oscillations. And what you see here, those are these little blippy things. Those are particles. Particles come early. They're faster than their emission. And this little pulse here that comes is the radio emission. Though this is how they were discovered, and clearly, with those technology, I can see how people in the 60s said, oh, this is never going to work. This is the LOFAR equivalent, fully digital and fancy triggers and everything. So technology has helped us a lot, but it's still a challenge because we can't integrate. You have a single pulse. You have a single shot at this, and you see here, the scale is in microseconds, so it's over in far less than a microsecond. So, and then the other problem is, unfortunately, a lot of things make radio pulses. So if you just set out to look for radio pulses, you would find a lot of things. And this is something that I brought sort of from my neutrino world. This is a plot where every dot here corresponds to one trigger, and this experiment only triggers roughly every minute. So, and the correlation here, this is a template search looking for the signal correlation that you expect from air showers and telling you that all the purple ones here are the cosmic rays and all the white ones are not. But you see all these stripes in here. These are sort of all the radio interference you get the radio noise, and you get all of this. So there's a lot of stuff going on. Why we can't just take SKA and say, go detect air showers, but we need to do a little bit more because otherwise we'll be swamping all the data pipelines. So at the bottom, this is something that I, typically like to show people just for an illustration. One of these is a cosmic rays and the other one is not. So, by eye, we can, if you're in the room, you can do a show of hands. People usually get it 50-50, but you do need sort of aggressive data analysis methods to actually tell these apart. And then just to, spoiler alert, that one is no cosmic rays and the other one is a cosmic ray. So that's why we can't just go to SKA and say, hey, let's get to it. And we learned a lot of it from SKA on our way, for SKA from our way to LOFAR. And one is that one should always get your users involved very early in software development, because you really, as I said with the lightning thing, you don't know what you need until you actually know what you can do. So it's this continuous back and forth, and then, we should probably change this. So I think right now the biggest advances instruments can make is then through actually, and I mean not only just software as in the fifth data analysis pipeline, but being relatively close to the instrument, sort of on the, what can you do directly on the electronics and these things that are going on. So if you do that early enough, you get lots of cool input, and that gives you lots of opportunities. And then one thing, I don't know, I should put this in bold and blinking or something. Do not ever underestimate the challenge in understanding the antenna. So LOFAR started operations in 2011, and I think I can publicly say that for the low-band antennas, there's still no good beam model. There is a beam model, but we know it doesn't work perfectly. So there's these known issues of mutual coupling between closed antennas that you can sort of reproduce in simulations, but not really well. And reproducing them comes at a high compute cost. We know that the shape of our element beam does not match the data. There's presumably some strange interplay going on between the LNA and the antenna, but also that is not really figured out yet. And then there's certainly an unmodeled temperature and potentially ground condition dependence on top of this. So despite everybody saying, hey, we do this instrument with a super easy and nice antenna and it's going to be great, do not ever underestimate the challenge in understanding the antennas, and the same is going to hold for the SKA antennas. The Scala antennas, SKA low is going to use, they're great. I really like them. But when people say, oh, they're log periodic dipole antennas, they're super easy, that's sort of when, I don't know, there's a little shiver crawling up my spine saying, well, did somebody just say antenna and easy? So I think this is one, from our perspective, one of the most important lessons for SKA. And why is that? Sort of because we're looking at these non-repeating pulses. We need to know every single instrument detail. We can't average over the whole sky. They come from the one direction they came from, and you better figure out what to do it. I think we've learned a lot about this, and sort of there's a lot of fun going on because we do galactic emission calibration and then basically looked at every single, what you see in the graph at the bottom, sort of detail of the system. So we looked at the LNAs, the coax cable, the receiver units, the ADC. So we, I think, turned everything upside down, which is, I think the upside of this is we can use our data, I think, ultimately to calibrate the instrument. So this is something that me, Justin, and Clancy, my colleagues, have written up on a small SKA note, sort of, how can we actually use the stuff that we're doing to make astronomers profit from this? And I think this is something that, it comes out of our work anyway. And at least at LOFAR, we're trying to combine this better at the moment. So let me, towards the end, close on sort of what's currently going on SKA. So we're working on our simulation studies, our analysis approaches, and these things. So I've shown you some LOFAR style analyses, but we can, of course, hopefully do better. We're working on this interferometric analysis, and I think hopefully, well, at some point, we should go there. We need a particle detector array for triggering. As I said, we can't just tell SKA go, so we need a particle array to trigger. So there's a prototype that exists at the MWA. We're working on integrating it into SKA's aperture verification station 3, and maybe we add muon detectors so we get more particle physicists excited. So we are really working a lot of engineering details, which makes us slightly different, I think, from many other science working groups. But for me, at least, it's been fun to do this and actually try to get in early and get technical details right early. So that brings me to my conclusion. So I've walked you through how we hope to get from LOFAR to the high precision measurements with SKA that we can then use for multi-messenger astronomy and particle physics. We hope to help get to the bottom of the sources of the cosmic rays. Sort of the radio detection is already leading in precision, but SKA really will knock it out of the park. And I left you the little colorful picture there. I just love it so much. That's great. It may also help in understanding air showers, discovering particle physics at the highest energy, which I think makes SKA also a great sort of instrument that actually sort of does have interdisciplinary aspects, even though it's mostly targeted for radio astronomy. So thank you all for listening, and I'm happy to take questions.
Thank you very much, Anna, for this wonderful talk. So now the talk is open for questions, and questions will be managed by Marilu Gendron. Please, Marilu.
Hi, can you guys hear me? I think so, yeah. Yes.
Okay, yes.
Thank you, Anna, for this amazing talk. I'm just like really impressed. It's like opening a completely new door for me. So yeah, so please in the Zoom, if you have a question, you can raise your hand, or I see Rainer, you can go ahead.
Hi, yes, thanks a lot for the talk. I couldn't be further from your field, and I usually find astroparticles very boring, but I found your talk very exciting. So that is the first thing I want to say. I've learned an immense amount of things, and it has been entertaining to listen to it. So
thank you very much.
I have a question, so two questions. So you could, with LOFAR, so basically you say you could understand hadronic interaction models better potentially. So that would be basically very basic nuclear physics, correct?
Yes. So that's our reason for, with LOFAR, we don't quite have enough antennas. We're working on this, but sort of this is a SKA, this one is an SKA figure. So we're really targeting with SKA to understand basic hadronic particle physics. Yes.
Cool. And for the lightning, I didn't get completely, so, but the lightning, that is just the electromagnetic emission from the lightning bolts themselves. It's not air showers, right? That you measure there to get the structure
so
of the lightning.
it's two things. So we basically got to it that our air shower signals look different because the electric fields change the charge separation. But then we actually looked at the lightning itself. But so interestingly, so if you said the lightning bolt, what we know as the lightning is just here in this figure, what's labeled return stroke. Mm-hmm. This is just what we see is sort of this one thing that connects to the ground that then sort of lights up. But the lightning is actually much, much bigger because it has all these channels in the clouds that is moving through that you cannot really see by eye, or in optical at least. So that's why, you know, we image the lightning, but we image a lot of the lightning that you otherwise can't see.
That's amazing. I don't know whether we have lightning people here at the Institute. I don't know whether they're here. They would love this. So thank you very much. Great talk.
Thank you.
I see Anston, you have your hands raised.
Hello, good morning. It was really a very interesting talk. I have learned a lot. That's the first thing I want to say. And just a curiosity, you mentioned that with SKA, you will be able to resolve the shape of the shower and also the clumpiness, but you haven't commented on this clumpiness. Can you give more details and the information you can get from it? So,
I mean, there's this is sort of something that usually where particle physics get sort of a little bit excited is sort of what when normal showers are considered, they're supposed to just be smooth. Like you know, you have your leading pions and then it's a very smooth development. But if you had like a weird new particle in there, what would happen is that sort of it's generated, it carries on some energy and then it starts to decay. So if you actually were able to take the shower in, you would see like a first lump and then a second clump, so to say. And people have tried doing this in Auger with fluorescence detectors to actually study for this, to look for new beyond standard model particle physics. But the problem is that usually if you do it sort of with fluorescence light, then usually if you see a clumpiness, you have a cloud or an aerosol contamination or something. So that lets it look as if there was like a first bump in your shower and then a second bump in your shower. So this is what we hope to overcome with radio, that we look for these rare showers that actually show like a double hump structure, so to say, and that would hint at potentially beyond standard model particle physics, or even at something in the standard model that we don't understand quite right.
Thanks a lot.
Delhi, you are next.
Yeah, thanks very much for a really good talk. I also learned a lot. I was curious about your simulations with the SKA. I know it's not popular to currently call things phase one and then full SKA, but I was curious if these simulations were done with what's projected for example, the telescope layout in 2028, 29, 2030, or is it even further down the road?
So we do our simulations with sort of everything there is. But the interesting thing is sort of I'm not 100% sure, but I thought sort of when we talk about phase one, phase two, and phase three, it's more adding like more remote stations that sort of all the plans have that the core will be built early. And we typically only use the core sort of, or the extended core. So that means I think for us, it doesn't make such a difference if it's, you know, phase one, phase two, phase three, because everybody says the core has highest priority, but we just use all the antenna positions at this point.
Okay, great. Thanks.
All right, other questions? Just raise your hand. I don't see any right now.
No, that's great. It's always great to hear when people learn a lot. So then I have my task fulfilled.
Yeah, but I have many different questions, but maybe I can go ahead with one. So you said that I'm not sure I understood if they are rare, these events, these air shower, like in one day, like can you observe many? What's like the scale?
Roughly 20 per day.
Okay.
So it depends. So it's if you look at the spectrum, it's sort of it falls very steeply with energy. So it's here multiplied by energy squared. So that means it would be even steeper. So, and LOFAR sort of, we start detecting them with LOFAR sort of around here. So, and they're the ones that come roughly every hour. But if you're interested in even higher energies, then, you know, you go an order of magnitude up in energy and you go a factor of e to the -3 down. So then they are rare. And even like the rarest ones here, Auger, which has a size of, I think, 3,000 square kilometers. It's taken them, I don't know, 10 years to measure 1 or 2. So depending on energy, they can get very, very rare, but we're starting sort of here in this mid-range where, you know, you can get 20 a day.
I see. And then with these like particle detectors right next to the telescope, you want to trigger that, right? So I guess these detectors also measure energy, and so you're like, okay, so this is a super energetic event, we need to observe it, something like that. Does it work like that?
Yeah, so what we do, we sort of switch them in coincidence. It's sort of the bigger shower, sort of the larger it triggers at the same time. So you take 2 particle detectors and you put them very far away and just say, okay, if you measure a signal at the same time, then you need to send a trigger. And they can be, the advantage is nothing else makes particles. So there's no background here that, you know, there's not like a dog barking and particles come out.
Yeah.
So you can use very, very simple particle detectors just as a trigger. So they don't give you a lot of information about the shower. They just told you, hey, I measured, I don't know, 2 muons and an electron. So then you can say, okay, as a trigger, this is plenty of information. You can, of course, think about beefing this up. And this is, I think, what I sort of put here, is that we can think of potentially shielded detectors for muon measurements. So you can, these are very simple. It's just plastic scintillator with a couple of silicon PMs to read them out. You can make them more complicated, so they'll tell you really how many particles and what flux, and you could use this as an independent measure. But you can also just go for the variant that says, oh, we just need it as a trigger so that we don't send readouts to SKA, swamp the data pipeline for something that's not worth it.
That's it. And if I may, I don't see any more questions. I will continue with one last. So I understand that this technique is good to understand the energetic or reconstruction and the mass and all of these things. But what about where they come from in the sky, like the spatial resolution, I guess, something like that?
So from an astronomy perspective, we're terrible. So we can do sort of half a degree, which usually by astronomy is like, you know, where your telescope's pointing. But the arrival direction itself also doesn't tell you so much on a fine scale because they're charged particles. So that means anyway, you know, to that degree, there's probably from the extragalactic or galactic sources, there's a deviation from a couple of degrees anyway from the source because the charged particle has been deviated in the magnetic field. So you know, there's not such a huge focus on this because they'll help us with global anisotropy, but for global anisotropy, 1 degree or half a degree is plenty.
Yeah, okay, I see. All right, thank you so much for the answers. Mike, let's see, Mike has a question. Okay, go ahead.
Hello, do you hear me?
Yes, we can hear you.
Okay, thank you very much for this very interesting talk. I have a question. Will SKA be able to measure and to refine neutrino masses?
So neutrinos. There is, so for neutrinos, you have the problem that the neutrinos still think our Earth atmosphere are transparent. So that means neutrinos never interact as air showers in the atmosphere, or they do, but then they have to come in very, very horizontally. And when they come in very, very horizontally, you have to project the SKA size sort of into this plane, and then it becomes tiny. So for very horizontal signals, SKA can in principle measure it, but it's probably going to be too small. And for other air showers, you don't see it. It's typically, you know, you need to be in ice or something to do this. However, there is the other sort of alternative, and this is what colleagues of mine work on, is you form beams on the moon. And you basically look at, if you're from the moon, if you have neutrinos coming through the rim of the moon, making showers in the lunar regolith, and then having sort of pulses coming towards Earth. It has a relatively high energy threshold, and there are a couple of projects like New Moon using the Parkes telescope, and also Westerbork and LOFAR have been used. So that is something I think still on the ticket for SKA, but this is not my field of expertise. So this could be an aspect of how SKA would measure neutrinos. But I build my neutrino detectors in ice, because then they all interact and they make radio emission in ice via a similar effect, and then I see them in ice. So this is the route I'm following.
Okay, thank you.
Thank you. And Dulcie, other question?
If there are no more questions, we can close the talk.
Yes.
Okay. Oh, one more here.
One more here from Kelly.
Yeah, sorry, I'm coming in late. I was curious, since someone asked about astrophysical directions and stuff, do you have any reason to expect that you might see a higher density of air showers towards the galaxy as opposed to extragalactic sources?
Yes, so but that's also an energy dependent effect, I think. That sort of, when you go to lower energies, we're quite certain that galactic cosmic rays are going to dominate. That's sort of, I don't know, I tend to the 14, 15 electron volts or so. Galactic sources will certainly dominate. And there's a lot of discussion sort of going on about maybe cosmic rays are somehow trapped in the magnetic field in the galaxies or re-accelerated in the halo or something. So at those low energies, I think there's it's quite certain that the galaxy, we see more from the galaxy than we do extra galactic. But when you move higher up in energy, sort of in this transition region where we are with LOFAR, it's really somewhere there the transition should happen from dominantly galactic cosmic rays to the extragalactic cosmic rays. And this is known by, I think most prominently by the measurement by Auger, showing that you measure an anisotropy. And the anisotropy you can only explain by the sources being extragalactic, with sort of the Earth moving in the in interstellar space rather than in the galaxy. So we know that at the highest energies, they have to be extragalactic. So they have to be, I don't know, maybe AGNs or something. And then at the lower energies, galactic. And then somewhere in this transition region, this is where SKA and LOFAR are great. And there the composition helps, because you expect sort of, I don't know, that it changes from, if you're proton dominated, that should be from somewhere else than if it's iron dominated or something. So this is where the detailed measurements will help us understand how this transition from galactic to extragalactic actually takes place.
Thanks very much.
Thank you. One last question, or? I don't see any. So René, if you want to conclude.
Okay, thank you very much again, Anna, for this wonderful talk. And everybody, see you in the next week on next talk, next colloquium. Thank you very much.
Thank you.
Okay, we are off the record now.